Early 1945, Japanese waters. The early morning haze over the waters off Japan's coast was broken only by the distant roar of engines and the occasional ripple of patrol boats slicing through the Pacific. A lone F4U Corsair, gleaming with the markings of the United States Marine Corps, fought a losing battle against its own mechanical failure. Its massive Pratt & Whitney R2800 Double Wasp engine, a marvel of American engineering capable of over 2,000 horsepower, stuttered and coughed before seizing entirely. The fighter, one of the most advanced aircraft deployed in the Pacific theater, began an uncontrolled descent toward the frigid waters below. Inside the cockpit, the pilot's hands moved with precision born of training and instinct. He was no stranger to danger. Months of combat across the Solomon Islands, the Philippines, and even Japanese-occupied islands had honed his reflexes. But this time, there would be no dogfight, no evasive maneuvers, no tactical dive to outpace a zero. This was a battle with physics and fate. With the engine dead, the Corsair became a plummeting projectile, the wind screaming past the canopy as the water loomed closer. Seconds felt like minutes. The pilot pulled the ejector handle, feeling the harness release and the seat spring him free. Below, the fighter struck the Pacific with a shuddering crash, sending icy spray into the dawn sky. The aircraft's fuselage shuddered, then settled, bobbing in the swells like a wounded bird. Twisted metal and floating debris marked its path, yet remarkably, large portions of the airframe remained intact. The cockpit canopy, wings, and landing gear, though damaged, had survived the impact better than anyone might have expected. For the pilot, rescue was immediate in his mind, but the war had placed him squarely within enemy-controlled waters. The vast expanse of the Pacific suddenly felt both endless and terrifyingly small. Within hours, the silence of the ocean was broken by the approach of Japanese patrol craft. These vessels, designed for coastal defense and anti-submarine operations, had been dispatched in response to reports of the downed fighter. They converged on the floating wreckage with practiced efficiency, their crews trained to salvage whatever intelligence the Americans left behind. For Japan, the recovery of an American fighter in such condition was not merely a tactical opportunity, it was a potential strategic windfall. In nearly 3 years of Pacific combat, Japanese pilots had faced the Corsair in countless dogfights. They had learned to respect its speed, its maneuverability, its devastating firepower, and the near-impervious construction that allowed it to absorb damage lethal to lighter aircraft. But until this day, they had never possessed an intact example, one they could handle, measure, and study with care. The patrol crews approached cautiously. They had been briefed to treat the wreck with extreme care. Any structural collapse or misstep could render the aircraft useless for technical analysis. Divers were deployed to ensure that submerged portions of the fighter were stabilized, lines were secured, and floating wreckage could be transported safely. Over the course of several hours, the Corsair was hoisted onto one of the patrol boats, the vessel's deck groaning under the combined weight of metal, machinery, and promise. To the sailors and technical personnel, this was no ordinary recovery. They had captured not just an aircraft, but a concentrated embodiment of American industrial power and technological innovation. For Japanese aviation specialists, the significance of this find would soon become clear. Over the preceding years, Japanese pilots had encountered Corsairs in aerial engagements across the Solomon Islands, Rabaul, and the Philippines, witnessing firsthand the fighter's superior climb rate, its ability to outpace and outdive Zeros, and its devastating armament of 6 Browning .50 caliber machine guns. These encounters had been fleeting, a few seconds of high-speed maneuvering and gunfire before the enemy vanished over the horizon. Now for the first time, engineers could examine the aircraft at their leisure, study the construction of its fuselage, wings, and engine, and measure the tolerances and precision that allowed such a machine to dominate the skies. The patrol boats made for a secure Japanese facility, where the Corsair would be unloaded and prepared for more detailed analysis. This moment marked the beginning of an extraordinary technical study, one that would reveal the true extent of the technological chasm between American and Japanese aviation by 1945. In the hands of Japanese engineers, the fighter was more than scrap metal. It was a window into a nation's industrial philosophy, a tangible demonstration of meticulous design, quality control, and manufacturing capability, concepts Japan had struggled to replicate under the pressures of war. While for the downed pilot the incident was a personal brush with mortality, for Japan, the Corsair represented a new form of revelation. It symbolized the full might of American industrial might, the combination of ingenuity, production capacity, and scientific advancement that Japanese engineers had long admired, feared, and now had the opportunity to scrutinize. The floating wreck had traveled from a moment of mechanical failure to become a cornerstone of technical intelligence, bridging the gap between battlefield experience and scientific understanding. The Corsair's arrival would not change the course of the war, but it would leave an indelible mark on Japanese aviation thought. Engineers, designers, and technical analysts could finally quantify what pilots had only felt, that American aircraft were faster, stronger, and built with a precision and consistency unmatched anywhere in the world. This single water-damaged fighter would illuminate the full scale of a technological and industrial challenge that Japan had been confronting for years, a challenge that had, by early 1945, become impossible to overcome. In the cold, still waters of Japan's coastline, the F4U Corsair rested, battered but intact, a silent testament to innovation, resilience, and industrial might. From the pilot's ejection to the Japanese patrol boat's careful retrieval, the aircraft's journey from combat casualty to intelligence treasure encapsulated the intersection of human skill, technological achievement, and the relentless tides of war. For Japan, it was a moment of reckoning, a confrontation with a reality that would shape both the final months of conflict and the post-war world that followed. The technological awakening. For the engineers and technicians of Japan's Naval Air Technical Arsenal at Yokosuka, the arrival of the F4U Corsair in early 1945 marked a moment of profound revelation. This was no ordinary intelligence acquisition. It was a confrontation with the tangible embodiment of American industrial and technological supremacy. The aircraft, recovered from the cold waters off Japan's coast, had survived impact, saltwater immersion, and enemy fire. Its structure, though battered, remained largely intact, a rare opportunity for Japanese specialists to dissect, measure, and understand a frontline fighter without the distortions introduced by battle damage. From the moment the Corsair was rolled into the secure examination hangars, the atmosphere was electric with anticipation. Groups of engineers, aeronautical designers, metallurgists, and aircraft technicians circled the aircraft, their eyes scanning the smooth fuselage, the inverted gull wings, and the massive 13-foot, 4-inch diameter propeller. Every detail demanded attention: rivet patterns, panel seams, engine mountings, control linkages, and cockpit instrumentation. This was more than an aircraft. It was a comprehensive lesson in design philosophy, material application, and manufacturing precision, a concentrated textbook of American aviation expertise. Japanese specialists had encountered American aircraft before, but mostly as wreckage, incomplete, or heavily damaged. The intact Corsair, however, revealed nuances and subtleties previously hidden. The first revelation came with the airframe itself. The fuselage's monocoque construction, combining lightweight aluminum alloys with structural reinforcements in high-stress areas, displayed a level of engineering rigor that Japanese designers had rarely seen. Measurements confirmed minimal tolerances and consistent dimensional accuracy across components, something Japanese wartime factories struggled to maintain under resource shortages and constant Allied bombing. The very skeleton of the Corsair was an artifact of industrial discipline, a structure designed not just to fly, but to survive, endure, and deliver consistent performance under extreme conditions. The inverted gull wing design immediately drew attention. Japanese engineers recognized the aerodynamic efficiency it provided, allowing the massive propeller to rotate without overly long landing gear while maintaining optimal airflow over the wings. More striking, however, was the execution. Each wing panel, each spar, each aileron and flap control surface was manufactured with precision, exhibiting identical dimensions and alignment, a feat of quality control that Japan's increasingly strained aviation industry could rarely replicate. Even the portions of the wing covered in fabric rather than metal, a deliberate design choice to save weight, were perfectly tensioned, weatherproofed, and integrated seamlessly into the airframe. To Japanese engineers, this demonstrated an advanced understanding of resource allocation, structural load distribution, and performance optimization, all executed with industrial consistency. The engine was the next revelation. The massive Pratt & Whitney R2800 Double Wasp radial engine, capable of over 2,000 horsepower, represented the pinnacle of American piston engine design. Disassembly revealed cylinders machined to tolerances measured in thousandths of an inch, pistons and connecting rods forged for durability, and a dual-row radial configuration balanced for vibration reduction and high-power output. The supercharger system, designed to maintain performance at high altitudes, featured precisely crafted internal passages and rotating components that operated with remarkable reliability. Japanese engine manufacturers, who had encountered similar systems in theory, were astonished at the quality of execution. The Corsair's engine did not merely function, it thrived under conditions that would have rapidly degraded comparable Japanese power plants. Armament and fire control systems further emphasized the technological gap. The Corsair's 6 Browning .50 caliber machine guns were mounted with precise alignment, fed through integrated ammunition systems, and connected to trigger mechanisms that ensured reliability even in extreme maneuvers. Japanese technicians noted the sophistication of the ammunition feed, the quality of barrel construction, and the standardization of components, all indicative of decades of mass production refinement. The armor plating around the cockpit, the bullet-resistant glass, and the carefully balanced distribution of weight revealed an American design philosophy that integrated pilot survivability without compromising performance, a balance that Japanese fighters, focused on lightness and maneuverability, struggled to achieve. Beyond individual components, the Corsair represented systemic industrial advantage. Every assembly, every component, every fastener reflected manufacturing discipline, process standardization, and rigorous quality control. Japanese engineers realized that what they were seeing was not just superior design, but the product of a national industrial ecosystem, one capable of producing complex, reliable high-performance machines at scale. The war had forced Japanese factories to prioritize quantity over quality, and materials were increasingly substituted due to shortages. In contrast, the Corsair's consistency in materials, machining, and assembly exemplified what decades of investment in research, tooling, and skilled labor could achieve. As the technical teams measured wingspans, disassembled control surfaces, and examined engine tolerances, a sobering truth emerged. The F4U Corsair was not just faster, stronger, and more heavily armed than Japan's frontline fighters. It was a symbol of the technological chasm that had opened between the two nations. Pilots had felt the Corsair's superiority in the skies, but the engineering teams now understood why. It was the result of superior industrial capacity, meticulous manufacturing, and a holistic design philosophy that integrated power, protection, armament, and operational flexibility. For Japan, this moment of technological awakening was a reckoning. It illustrated how far the nation had fallen behind in aviation technology and industrial capability, despite decades of innovation. The intact Corsair was both a marvel and a mirror, reflecting what Japan could have achieved under conditions of industrial abundance, quality control, and resource security. It was a lesson too late to alter the course of the war, but one that would resonate deeply in the post-war reconstruction of Japanese industry and engineering. The F4U Corsair, once a feared adversary in the skies, had become a teacher in the hangar. The birth of the Corsair, 1938 to 1940. The story of the F4U Corsair begins in 1938, when the United States Navy recognized the pressing need for a high-performance fighter capable of outmatching emerging threats in the Pacific. The Navy's Bureau of Aeronautics issued a specification that seemed almost audacious at the time, a carrier-based fighter capable of exceeding 400 miles per hour in level flight. Most fighters of the late 1930s struggled to break 350 miles per hour, and many could barely sustain such speeds without compromising maneuverability or structural integrity. The challenge was monumental: speed, range, armament, and carrier suitability, all to be balanced in a single design. Chance Vought, a company already known for innovation, accepted the challenge. Chief designer Rex Beisel approached the problem with a revolutionary mindset. Unlike contemporary designs that attempted to squeeze performance from standard engines, Beisel and his team decided to build the aircraft around the most powerful engine available, the Pratt & Whitney R2800 Double Wasp. This radial engine was an engineering marvel, boasting 18 cylinders arranged in 2 rows of 9, producing over 2,000 horsepower, almost twice that of most fighters in service. The engine alone promised unprecedented speed and climb rates, but it also introduced a host of engineering complications. The sheer power of the R2800 demanded a propeller capable of absorbing that energy. Beisel's team designed a massive 13-foot, 4-inch diameter propeller, the largest ever fitted to a fighter aircraft at the time. Such a propeller presented an immediate problem: how to prevent it from striking the deck of an aircraft carrier during takeoff and landing while keeping the aircraft's landing gear practical and robust. The solution would become the Corsair's most distinctive and recognizable feature, the inverted gull wing. Unlike conventional straight wings, the Corsair's wings bent downward from the fuselage and then leveled out toward the tips, creating an M-shaped profile when viewed head-on. This design allowed shorter, sturdier landing gear while maintaining proper ground clearance for the massive propeller. Beyond its practical application, the inverted gull wing also offered aerodynamic advantages. The anhedral angle at the wing root minimized interference drag, while the overall wing shape optimized airflow for lift and speed. The design was elegant, functional, and daring, a bold departure from contemporary engineering norms. Construction began rapidly. The F4U prototype emerged as a sleek, almost aggressive silhouette. Its fuselage, a combination of lightweight aluminum alloys reinforced in high-stress zones, reflected a meticulous attention to weight distribution and structural integrity. Every component was engineered for performance without compromise. The control surfaces, ailerons, elevators, and rudder were balanced for precision responsiveness at both low and high speeds. Armor was minimal, to save weight, but strategically placed to protect critical components such as the pilot and engine. On May 29, 1940, the F4U took to the skies for the first time, piloted by Lyman Abelard Jr., the factory's chief test pilot. Observers watched as the Corsair climbed, banked, and accelerated with unprecedented power and grace. The prototype's performance exceeded expectations. By October 1, 1940, during a test flight between Stratford and Hartford, the F4U achieved a ground speed of 405 miles per hour aided by a tailwind, setting a new benchmark for single-engine fighters in the United States. The aircraft's maximum level flight speed, measured at 378 miles per hour at 23,500 feet, was equally impressive, signaling that this was not merely a fast plane on paper, it was a machine capable of dominating the skies. The Corsair's early promise quickly translated into production planning. Vought engineers and Navy officials worked to refine the design, balancing structural reinforcements, armament configurations, and carrier compatibility. The aircraft's 6.50 caliber Browning machine guns, integrated into the wings, provided devastating firepower, while the rugged landing gear and reinforced airframe made it suitable for operations from the rough and hastily constructed airstrips often used in the Pacific. By late 1942, production F4U Corsairs were rolling off assembly lines and reaching operational units. Marine Fighter Squadron 5, VMF-5, became one of the first squadrons to deploy with the Corsair. On February 12, 1943, the unit arrived at Henderson Field on Guadalcanal, a strategic airfield contested by Japanese forces. The Corsair's arrival marked a significant shift in aerial capability for the Marines. The aircraft combined speed, firepower, and durability in a way that few Japanese pilots had encountered before. While its initial combat engagement, later dubbed the St. Valentine's Day Massacre, was challenging, early combat experiences demonstrated the Corsair's potential for boom and zoom tactics, hit-and-run engagements, and survivability under fire. By the end of 1940, the Corsair had already established its reputation as a technological marvel. Its radical design, centered around the powerful R2800 engine and supported by the innovative inverted gull wing, was a triumph of engineering foresight. It foreshadowed the evolution of American naval aviation doctrine, emphasizing speed, firepower, and adaptability. The lessons learned during these formative years, prototype development, flight testing, and early operational deployment, would define the Corsair's legendary service record throughout the Pacific War. In essence, the birth of the Corsair was a convergence of vision, engineering audacity, and industrial capability. It was not merely an aircraft, it was a statement that through innovation, precision, and determination, American designers could create a fighter capable of rewriting the rules of aerial combat. Early combat and tactical adaptation. The F4U Corsair entered combat with a reputation yet to be proven in the crucible of war. Its design was revolutionary, its performance unmatched by any American fighter of the time, but raw technological superiority alone could not guarantee success in the chaotic and unpredictable environment of aerial warfare. That lesson became painfully clear on February 14, 1943, an engagement that would later be remembered by Marines and historians as the St. Valentine's Day Massacre. On that day, Marine Fighter Squadron 5, VMF-5, freshly deployed to Henderson Field on Guadalcanal, took the Corsair into battle against a formation of Japanese Zero fighters. The Corsair pilots, confident in their aircraft's speed, armament, and ruggedness, expected to dominate the skies. The Zero, however, was a fighter perfected for agility and low-speed maneuvering. As the two forces clashed over the tropical islands, reality struck hard. Within minutes, the engagement turned disastrous. 9 American aircraft, including 2 Corsairs, were lost to Japanese defenses, while the Japanese suffered the loss of only a single fighter. The disparity was stark. The Corsair, with its massive Pratt & Whitney R2800 engine, 6.50 caliber Browning machine guns, and near indestructible airframe, was theoretically superior in every measurable parameter. Yet, in practice, the American pilots had underestimated the tactical acumen and experience of their Japanese adversaries. The Zero's exceptional turning ability and lightweight design allowed it to exploit moments of Corsair vulnerability. In the dense, humid skies above Guadalcanal, raw speed could not always compensate for insufficient tactical awareness. This sobering encounter revealed an essential truth: technological advantage alone does not ensure victory. Combat success required not only powerful machinery but also a deep understanding of the operational environment, enemy capabilities, and tactical doctrine. American pilots quickly recognized that traditional dogfighting techniques, trading turns and rolls with the enemy, played into the Zero's strengths. New strategies would be required if the Corsair was to fulfill its potential. Thus began a period of rapid tactical adaptation. Flight instructors, squadron leaders, and test pilots worked tirelessly to develop combat maneuvers that leveraged the Corsair's unique characteristics. The key lay in speed, altitude, and energy management. Pilots discovered that by maintaining a higher altitude than their opponents, they could convert potential energy into kinetic energy, diving onto enemy aircraft with devastating speed. This tactic, later called boom and zoom, allowed Corsair pilots to strike quickly, unleash their powerful .50 caliber machine guns, and then disengage before the slower, more agile Zero could retaliate. Boom and zoom relied on precise timing and discipline. Pilots had to resist the temptation to turn with enemy aircraft, which would nullify the Corsair's speed advantage and expose them to deadly counterattacks. Instead, they learned to plan attacks from above, choosing the moment to dive, fire, and ascend again in one fluid motion. Altitude management became paramount, and situational awareness, knowing where every enemy fighter was at all times, was as critical as aiming the guns. The first pilots to master these tactics soon proved their effectiveness. Lieutenant Kenneth A. Walsh, a young Marine assigned to VMF 124, distinguished himself through exceptional skill and understanding of the Corsair's capabilities. On May 13, 1943, Walsh achieved his first aerial victories, becoming the first Corsair ace. Over the course of the war, he would tally an astonishing 21 confirmed kills. Walsh's success was not merely a testament to his personal skill. It reflected the Corsair's strengths fully realized in the hands of a pilot who understood how to exploit its advantages. Beyond individual feats, the tactical evolution transformed squadron operations. Pilots coordinated attacks in pairs or small groups, using the Corsair's superior speed to strike multiple targets sequentially. Formation flying emphasized altitude preservation and energy conservation, allowing aircraft to disengage safely after each strike. Ground crews adapted rapidly as well, learning to maintain and repair the aircraft in tropical conditions, ensuring maximum availability for combat sorties. The lessons learned during the early engagements at Guadalcanal had profound implications for the Pacific War. The Corsair, when flown with proper tactics, could dominate the skies even against experienced Japanese pilots. Its combination of speed, firepower, and durability became a force multiplier. What had initially seemed like a catastrophic mismatch at the St. Valentine's Day massacre transformed into a model for effective air combat doctrine. By the end of 1943, Corsair pilots were routinely achieving superior kill ratios against Japanese aircraft. They had learned to respect the aircraft they flew, not merely as a tool, but as an extension of their own tactical skill. The F4U was no longer just a fast, heavily armed fighter. It was a precision instrument for aerial combat, capable of reshaping engagements through strategic application rather than brute force alone. The early combat experiences also underscored a crucial principle: the intersection of technology and tactics determines success. The Corsair's advanced design was remarkable, but without proper tactical adaptation, it could be vulnerable. Conversely, American pilots' ability to learn, adjust, and innovate allowed the Corsair to realize its full potential. This period of rapid evolution, marked by trial, error, and eventual mastery, laid the groundwork for the Corsair's legendary status in the Pacific, proving that superior aircraft, when combined with superior tactics, could decisively shift the balance of power in aerial warfare. Combat reputation and versatility. By 1943 and 1944, the F4U Corsair had firmly established itself as one of the most formidable fighters in the Pacific theater. Its reputation was built not just on raw speed or advanced engineering, but on a combination of ruggedness, firepower, and adaptability that few Japanese pilots could match. In the dense tropical skies above the Solomon Islands, the Corsair quickly demonstrated its ability to survive combat conditions that would have destroyed lighter, more fragile aircraft. Even when sustaining battle damage, from enemy machine gun fire, shrapnel, or anti-aircraft flak, the Corsair's robust airframe, durable landing gear, and powerful engine often allowed pilots to return safely to base, bringing both themselves and valuable intelligence back to their squadrons. Central to the Corsair's early combat success were its 6 Browning M2.50 caliber machine guns. 4 of these were mounted inboard with 400 rounds each, and 2 outboard guns carried 375 rounds each, totaling 2,350 rounds of devastating firepower. The combination of rapid-fire capability, large caliber bullets, and carefully engineered gun harmonization allowed pilots to bring overwhelming force to bear on enemy aircraft, reducing Japanese Zeros and other fighters to little more than debris in the air. These guns were not just destructive, they were precise. Skilled Corsair pilots could target critical components like engines or control surfaces, incapacitating aircraft in seconds. The psychological effect on Japanese pilots was profound. From the cockpit of a Zero, the Corsair appeared indestructible, a machine that could strike and disappear before the enemy had a chance to react. By late 1943, Vought had introduced upgraded variants of the Corsair. The F4U-1C, for example, replaced the 6.50 caliber guns with 4 20mm cannons, providing an entirely different kind of firepower capable of tearing through the most heavily armored Japanese fighters. While some pilots preferred the high ammunition count and reliability of the .50 caliber guns, the cannons offered the ability to engage larger, slower-moving targets or fortified ground positions with devastating effect. This flexibility underscored a critical characteristic of the Corsair, its versatility. It was not limited to dogfighting or air superiority missions. It could serve as an effective fighter bomber, providing close air support where traditional aircraft might struggle. By mid-1944, the Corsair's versatility became even more pronounced. Pilots were routinely equipping their aircraft with external ordnance, including 1,000-pound bombs on the centerline or wing racks, high-velocity rockets, and even napalm canisters for attacking entrenched ground positions. The ability to switch from air-to-air combat to ground attack without fundamentally altering tactics or configuration made the Corsair indispensable during amphibious operations and island-hopping campaigns. During the Okinawa campaign of 1945, Corsairs flew thousands of close air support sorties, providing what infantrymen described as heaven-sent support, earning the aircraft the evocative nickname Angels of Okinawa. The pilots of the ground forces knew that when a Corsair appeared overhead, their assault had immediate and overwhelming backing, capable of destroying pillboxes, artillery emplacements, and troop concentrations with terrifying efficiency. From the perspective of Japanese pilots, much of the Corsair's reputation was apparent. The aircraft was fast, resilient, and heavily armed. Pilots in Zeros or other fighters quickly learned that engaging a Corsair in a turning fight was a losing proposition. The Corsair could climb rapidly, dive at tremendous speeds, and maintain energy advantage in ways Japanese aircraft could not match. Yet what remained hidden from them was the engineering brilliance behind the aircraft. Only through later physical examination could Japanese engineers fully appreciate the sophistication of the Corsair's construction, the meticulous metallurgy of its airframe, the balanced combination of metal and fabric in non-critical areas to reduce weight, and the integration of a massive 18-cylinder Pratt & Whitney R2800 Double Wasp engine capable of producing over 2,000 horsepower. Even in battle, these design features contributed indirectly to the Corsair's combat reputation. Its inverted gullwing design allowed for short, durable landing gear suitable for rugged forward airstrips, while providing clearance for the enormous 13-foot propeller, a necessity to harness the full power of the engine. The engine itself could endure prolonged combat operations under high stress, and the airframe absorbed significant damage without catastrophic failure. Japanese pilots often misinterpreted this as near-magical invincibility, unaware that it was the result of deliberate design choices and superior American manufacturing standards, not luck. The Corsair's adaptability extended to tactics as well. Pilots learned to exploit its strengths across diverse combat scenarios. In air-to-air engagements, boom and zoom tactics leveraged speed and energy. In ground attacks, precise delivery of bombs, rockets, or napalm allowed for maximum destructive effect while minimizing exposure to anti-aircraft fire. The aircraft's combination of speed, firepower, and survivability made it a multi-role weapon long before the concept became standard in post-war military aviation. By the end of 1944, the Corsair had earned a fearsome reputation not only among the Japanese but across the Pacific theater. It was feared, respected, and relied upon in equal measure. Ground forces came to see it as a near-omnipotent ally, while pilots recognized that mastery of the aircraft and its tactics could decisively influence the outcome of engagements. Yet the full story of the Corsair's superiority, its engineering, manufacturing precision, and thoughtful integration of systems, remained invisible from the cockpit. Only when captured examples were examined in Japanese facilities could the full technological sophistication be understood, revealing a gap in industrial capability that no tactical adaptation could overcome. The F4U Corsair thus embodied a dual legacy. In the skies, it was a formidable combatant capable of overwhelming Japanese aircraft and supporting ground operations with unmatched effectiveness. Behind the scenes, it represented the pinnacle of American wartime engineering and industrial power, a fact that would be confirmed when Japanese specialists finally dissected captured examples in 1945. The Corsair's versatility, ruggedness, and firepower had made it legendary, but its engineering brilliance secured its place in history as one of the most successful and influential fighters of World War II. Japanese technical facilities. Japan's ability to gain insights into Allied aircraft relied heavily on its technical and research infrastructure, which had been developed and refined over decades. By the time the war reached its final stages in 1945, the Japanese aviation establishment possessed two primary centers for the study and analysis of captured aircraft: the Yokosuka Naval Air Technical Arsenal, located south of Tokyo, and the Tachikawa Army Aviation Technical Research Institute. Both facilities were staffed with highly trained engineers, designers, and technicians who had spent years attempting to reverse engineer or extract intelligence from downed or captured Allied aircraft. The Yokosuka Naval Air Technical Arsenal, officially reorganized in April 1932 as the Kaigun Kakusho Naval Air Arsenal, had evolved into Japan's premier naval aviation research facility. Its mission extended beyond design. It included meticulous examination of aircraft performance, structural design, materials, and systems integration. Thousands of skilled engineers worked in various departments, from metallurgy and propulsion to aerodynamics and weapons integration. Over the course of the war, Yokosuka had examined numerous Allied aircraft, often salvaged from crash sites in the Pacific or returned from local airstrips. While these studies provided incremental intelligence, the majority of captured aircraft were heavily damaged, missing critical components, or degraded by combat and environmental exposure, limiting the value of technical analysis. Similarly, the Tachikawa Army Aviation Technical Research Institute served the Imperial Army's aviation arm. Its personnel specialized in studying foreign aircraft designs, reverse engineering mechanical systems, and attempting to incorporate these insights into domestic aircraft production. Like Yokosuka, Tachikawa faced a persistent problem: the scarcity of complete, intact specimens. By late 1944, wartime conditions, intensifying air raids, supply shortages, and rapid retreat from forward positions, had made it increasingly difficult to recover aircraft in good condition. This reality made the arrival of an intact F4U Corsair in early 1945 exceptionally significant. The Corsair, salvaged from waters off the Japanese coast after a forced ditching, represented a rare opportunity to examine a frontline Allied fighter in near-operational condition. Unlike previous captures, this aircraft had suffered minimal combat damage, and careful handling during recovery ensured that most critical systems remained intact. Japanese engineers quickly realized the strategic value of this acquisition. Unlike observations from aerial encounters, which could only reveal general performance, silhouette, and behavior, the physical aircraft allowed detailed study of engineering methods, material choices, and manufacturing precision, offering insights that would have been impossible to glean from battle alone. Upon arrival at Yokosuka, the Corsair was transported to a secure technical area, where the meticulous process of documentation and examination began. Engineers approached the aircraft systematically. Every component, from the fuselage to the smallest fasteners, was photographed and measured. The wingspan of 40 feet 11.7 inches, the fuselage length of 33 feet 4 inches, and the height of 15 feet with wings extended, 16 feet 2.3 inches with wings folded, were carefully noted. Measurements were cross-checked, and diagrams were created for reference. The inverted gull wing configuration, which had initially struck Japanese engineers as unconventional, was scrutinized for its aerodynamic benefits, structural efficiency, and manufacturing complexity. Beyond basic dimensions, engineers examined the materials and structural components of the Corsair. The wing structure, fuselage spars, and control surfaces were inspected for metallurgy, fabrication techniques, and assembly methods. They documented the combination of metal and fabric covering, noting that certain non-critical surfaces were intentionally covered with treated fabric rather than metal, a choice designed to reduce weight while maintaining strength. The precise tolerances, uniformity of components, and integration of systems reflected a level of industrial quality control that Japanese production increasingly struggled to achieve by 1945. The examination extended to mechanical and systems engineering. Engineers documented landing gear mechanisms, control linkages, cockpit instrumentation, fuel systems, and electrical wiring. Special attention was paid to the Pratt & Whitney R2800 Double Wasp engine, a powerhouse driving the Corsair's exceptional speed and climb performance. The engine's components, cylinders, pistons, crankshaft, and supercharger, were measured and photographed. Each component revealed meticulous machining, precision tolerances, and high-quality materials, all contributing to remarkable reliability and power output. Even the Corsair's armament received detailed attention. Engineers noted the installation of 6 Browning M2.50 caliber machine guns, the placement of ammunition boxes, and the smooth integration of feed and ejection systems. The compact, functional design demonstrated not only firepower but also attention to maintainability and operational efficiency, something that Japanese factories increasingly struggled to match under wartime constraints. Every stage of inspection, photography, measurement, and written documentation highlighted the contrast between Japanese and American industrial capabilities. Where Japanese facilities were under constant pressure from resource shortages, bombing raids, and workforce depletion, the Corsair embodied the culmination of decades of American design philosophy, industrial precision, and quality control. For Japanese engineers, the aircraft served as both a technical study and a stark benchmark for the technological gap that had emerged during the war. The intact Corsair at Yokosuka represented more than a captured fighter. It was a lesson in industrial capability, engineering sophistication, and the cumulative power of a nation's manufacturing base. Through systematic analysis, Japanese specialists gained a profound understanding of American design principles, production methods, and material science, knowledge that would later influence post-war reconstruction and the modernization of Japanese aviation. In essence, the technical facilities at Yokosuka and Tachikawa transformed a single aircraft into a window into American industrial and engineering dominance, allowing Japanese engineers to witness firsthand the level of precision, planning, and resource allocation required to produce a fighter capable of outperforming their own aircraft across nearly every metric. Structural and aerodynamic insights. At the Yokosuka Naval Air Technical Arsenal, the captured F4U Corsair was rolled into one of Japan's most secure hangars. Under the dim light of inspection lamps, engineers and technicians gathered around the unfamiliar shape of the aircraft, a fusion of curves and steel unlike anything they had built. What immediately drew their attention was its most distinctive feature, the inverted gull wing. Unlike traditional straight wing or upward bent designs common in Japanese aircraft like the Zero or the Raiden, the Corsair's wings dipped gracefully downward before rising again toward the tips. It was a shape that looked almost artistic, yet every contour had purpose. The Japanese engineers began their study with the wing structure. They traced the sweep and angle, noting how the gull wing reduced drag while allowing the use of a massive 13-foot propeller without extending the landing gear to impractical lengths. The shape also provided a stronger root connection between wing and fuselage, distributing stress more efficiently during carrier landings. This was not an aesthetic flourish, it was a mathematical masterpiece. For the first time, the Japanese technicians understood that this seemingly complex shape represented the American balance of power, precision, and practicality. The surface materials of the Corsair surprised them even more. While much of the aircraft was made from advanced aluminum alloys, portions of the outer wing panels were covered in doped fabric. Initially, some engineers scoffed. Why would the Americans use such an outdated technique on a modern fighter? But upon closer inspection, they realized it was a deliberate act of design efficiency. The fabric section saved precious weight at the wingtips, reducing inertia and improving roll rate without compromising strength. The doped linen was stretched tight over the ribs, treated with compounds to resist moisture and vibration fatigue. It was light, strong, and brilliantly practical, a blend of innovation and tradition that reflected a deep understanding of aerodynamic trade-offs. Beneath those surfaces, the true engineering marvels came into view. When Japanese metallurgists cut open a section of the wing spar, they discovered precision-machined aluminum components unlike anything in their own factories. The spars were large, cleanly riveted, and reinforced with heat-treated alloy joints that displayed minimal warping. Every rivet was uniform, every seam exact. American production standards, even under mass wartime output, showed a level of quality control Japan could no longer sustain. Their own factories, under constant bombardment and resource shortages, had long resorted to using lower-grade steel and wood composites. The Corsair, by contrast, was an artifact of an industrial superpower at its peak. Aerodynamically, the Corsair's configuration represented an evolution in wartime design philosophy. Its fuselage was sleek yet muscular, with the engine cowling carefully contoured to minimize drag while maximizing airflow to the massive Pratt & Whitney R2800 engine. The Japanese engineers noted how the large air scoops and exhaust stacks were positioned to maintain pressure balance, a detail absent in many of their own aircraft, where cooling and aerodynamics often conflicted. The Corsair's fuselage also incorporated flush riveting and smooth transitions that gave it a refined aerodynamic efficiency. As the engineers tested control surfaces, they found balance tabs and aerodynamic compensators that reduced pilot workload. The ailerons and elevators moved with precision, counterweight to prevent flutter at high speeds. This kind of engineering sophistication was rare in Japanese fighters, which often prioritized agility over stability. The Corsair, by contrast, was built to dominate at high speed and high altitude, where stability meant survival. Japanese aerodynamicists measured the wing's laminar flow characteristics, recognizing its contribution to speed and climb performance. They were astonished by the calculated compromises. The wing's thick root provided space for landing gear and ammunition, while its thinner tips improved efficiency. Every inch was designed with intent. Nothing was wasted. When metallurgists examined samples from the airframe, they found alloys containing elements like nickel and chromium, metals Japan could no longer access in significant quantities due to Allied blockades. The purity and consistency of these materials explained why the Corsair could withstand immense stress, absorb battle damage, and still return home. The comparison was painful. Many Japanese aircraft of 1945, such as the Ki-84 and N-1K2, were excellent in concept but suffered from inferior materials and hurried construction. The Corsair, meanwhile, reflected the confidence of a nation unburdened by scarcity. Inside the cockpit, Japanese technicians documented every control, switch, and instrument. They were impressed by its ergonomics. Everything was within easy reach of the pilot. The layout emphasized functionality under combat stress. The sighting system was advanced, the visibility excellent, and the armor protection substantial. Even the pilot's seat harness and oxygen system reflected careful thought. Where Japanese fighters had sacrificed protection for agility, the Corsair achieved both survivability and lethality. As the study concluded, the Yokosuka engineers compiled a detailed report for the Naval General Staff. It concluded that the F4U Corsair represented not just an aircraft, but an entire ecosystem of industrial mastery. Designers, factories, materials, and machines working in perfect coordination. One engineer summarized it bluntly: "This fighter is not the product of genius alone, it is the product of abundance." For Japan's war planners, the Corsair was both an inspiration and a reminder of futility. No amount of technical analysis could bridge the gap that separated their wartime industry from America's. The inverted gullwing became a symbol of everything Japan could admire but not replicate, a graceful expression of aerodynamic logic forged by an empire of machines. In the months that followed, the Corsair's dissection deepened Japanese understanding of American air power. But by then, the war was nearing its end, and these insights arrived too late to change its course. The wrecked Corsair, once a fallen enemy, now rested quietly in a hangar, a silent witness to the technological awakening of a nation realizing the scale of its opponent's dominance. Armament and firepower. Inside the Yokosuka Naval Air Technical Arsenal, the Japanese engineers turned their attention next to the Corsair's wings, broad, muscular, and densely packed with weapons. What they found inside shocked even the most experienced among them. Each wing housed 3 Browning and /M 2.50 caliber machine guns, 6 in total, aligned with precise symmetry, their ammunition belts coiled like metallic serpents through feed chutes that spoke of mechanical perfection. The engineers had long been familiar with machine guns. Japan had its own arsenal of 7.7 mm and 13.2 mm aircraft weapons. Yet, What lay before them was something entirely different in philosophy and execution. The Browning M2s were not merely guns. They were the industrial expression of power, reliability, and mass production. Each weapon was a masterpiece of precision machining, capable of firing over 800 rounds per minute with astonishing consistency. The barrels gleamed under the inspection lights, the feed mechanisms moved with flawless alignment, and the synchronization between all 6 weapons reflected an extraordinary level of engineering coordination. When the Corsair's wings were opened for study, the Japanese weapons specialists took note of how efficiently space had been used. The compact arrangement of the guns allowed the Corsair to carry an enormous volume of ammunition, up to 2,350 rounds in total, without compromising aerodynamic balance. Ammunition belts were guided through feed trays that minimized jamming and overheating, while cooling vents and ejection chutes were placed with surgical precision. Everything about the installation demonstrated a meticulous understanding of combat endurance. In contrast, many Japanese fighters, such as the A6M0 or Ki-43 Hayabusa, were armed with lighter 7.7mm or 12.7mm weapons, which, while sufficient in the early years of the war, lacked the destructive power to penetrate the armor of American bombers or even to guarantee quick kills in dogfights. The Corsair's .50 caliber guns, by comparison, could shred through aircraft frames, pierce armored cockpits, and ignite fuel tanks in a single burst. Each round weighed more than twice that of a Japanese 7.7mm bullet and carried greater kinetic energy, giving the American pilot overwhelming fire superiority in every engagement. As they tested the weapon mounts, the Japanese examiners noticed how easily the Brownings could be removed and serviced. Every panel opened cleanly, allowing rapid maintenance and ammunition reloading. This was a revelation to technicians accustomed to tight, inefficient gun bays that required hours of labor to service. In the field, such efficiency meant that a Corsair could be rearmed and ready to fly again in under 30 minutes, a decisive advantage in high-tempo operations. But what truly astonished the Japanese engineers was not just the firepower itself, but how it was integrated into the broader philosophy of survivability. Beneath the armor plates surrounding the cockpit and the heavy bullet-resistant windscreen, they saw something rare in Japanese design, a deep concern for the pilot's protection. American designers had clearly accepted a slight performance penalty in exchange for keeping their pilots alive. The armor plating behind the pilot's seat was thick, contoured to deflect incoming rounds from below and behind, the most common attack angles in air combat. The bulletproof glass of the windscreen could withstand multiple hits from 7.7mm rounds, giving the pilot precious seconds to react or escape. For Japan's own aviation experts, who had built aircraft like the Zero under a different doctrine, favoring agility, speed, and range over protection, this was an uncomfortable realization. Their best fighters, while elegant and deadly in the hands of skilled pilots, were fragile. A few well-placed .50 caliber hits could tear through a Zero's frame or ignite its unprotected fuel tanks. In contrast, the Corsair could take damage, absorb punishment, and still bring its pilot home. The engineers examined the ammunition itself, cartridges meticulously crimped, the bullets seated with mathematical precision. Each round was a tiny piece of industrial art. Armor-piercing incendiary, tracer, and ball ammunition were alternated in the belts for maximum effect, allowing the pilot to both aim visually and ensure that every burst inflicted serious structural damage. The sheer uniformity of the ammunition told its own story. American industry could not only produce millions of these rounds per month, but also maintain near-perfect quality across all of them. In one corner of the hangar, a Japanese officer picked up a .50 caliber round and rolled it between his fingers. "Each of these," he murmured, "is a fragment of their factories." He wasn't wrong. Every bullet, every link in the feed belt, every firing mechanism represented the collective might of American manufacturing. The foundries, assembly lines, and inspection plants that ran around the clock without shortage or disruption. Japanese reports from the Yokosuka inspection later noted with grudging respect that the Browning M2's design was as much a triumph of simplicity as of engineering. Despite its power, the mechanism was straightforward, reliable under extreme conditions, and easy to mass-produce. Unlike Japan's more delicate weapon systems, the Browning could function in the humid jungles of the Pacific, the freezing altitudes of Korea, or the salt-laden air of carrier decks, all with minimal maintenance. Even the gun harmonization impressed them. American ground crews had perfected the art of aligning the 6 guns to converge at a precise point ahead of the aircraft, usually around 300 yards, creating a lethal cone of fire. A single 1-second burst could unleash nearly 100 rounds, tearing enemy aircraft apart before they could even react. By the end of their inspection, the Japanese technicians had reached a sobering conclusion. The Corsair's firepower wasn't just about killing power, it reflected a worldview. Where Japan sought elegance in combat, America sought efficiency. Where Japan emphasized the skill of the individual, America empowered that individual with machines of unmatched strength. The Corsair's 6 Brownings were the embodiment of that philosophy. They turned one man's reflexes into industrialized destruction, precision, reliability, and sheer volume fused into a single weapon system. As the engineers closed the inspection panels, one of them noted quietly in his report, "The enemy's greatest weapon is not this gun, nor this airplane, it is the factory that can build 1,000 more." Engine and propeller analysis. When Japanese engineers at the Yokosuka Naval Air Technical Arsenal finally removed the Corsair's cowling and exposed its heart, the Pratt & Whitney R2800 Double Wasp, they found themselves staring into a machine that symbolized everything Japan could not replicate. The engine was immense, a twin-row, 18-cylinder radial masterpiece that combined brute force with precision craftsmanship. To the untrained eye, it was just another radial engine. But to the technicians who had spent the war maintaining fragile, temperamental power plants under constant material shortages, this was something transcendent, a cathedral of metal and engineering discipline. The R2800 Double Wasp was unlike any power plant Japan had encountered. Its sheer presence filled the workspace, every cylinder meticulously aligned, every cooling fin machined with uniformity that seemed impossible under wartime conditions. Producing over 2,000 horsepower, this engine powered not only the Corsair but also the Thunderbolt and the Hellcat, aircraft that had dominated skies from the Solomons to Saipan. As the engineers dismantled its outer components, the deeper layers revealed a kind of perfection they rarely saw even in peacetime Japanese prototypes. The tolerances were exact. The casting of the crankcase, the balance of the pistons, the precision of the bearings, all spoke of an industrial culture that had mastered large-scale precision engineering. One Japanese report later described the engine as a symphony of standardized excellence. Unlike Japanese engines, which often relied on hand-fitting and individual craftsmanship to achieve tolerances, the R2800 components were interchangeable, an outcome only possible through advanced tooling, gauges, and quality control. This meant American factories could produce thousands of engines with identical performance, while Japanese plants still struggled to ensure consistency from one batch to the next. The engineers were particularly fascinated by the 2-stage, 2-speed supercharger system, a marvel of mechanical sophistication. It was this system that allowed the Corsair to maintain its performance at high altitudes, where most Japanese engines lost power rapidly. The supercharger compressed incoming air in 2 stages, driven by precisely machined gears that switched speeds automatically depending on altitude. This granted the Corsair immense versatility, letting it fight from sea level to over 30,000 feet without losing combat effectiveness. When the supercharger assembly was disassembled for closer inspection, the Japanese engineers noted the perfect symmetry of its impellers and the mirror-like surfaces of its inner walls. Such finishes could only be achieved through advanced machine tools and extensive quality assurance, resources Japan no longer possessed by 1945. Even more impressive was the cooling system. The Corsair's engine employed clever ducting and baffles to channel air evenly across the cylinders, preventing overheating during low-speed carrier operations or tropical ground idling. Japanese mechanics were accustomed to coaxing underpowered engines to survive long enough for combat. The R2800, by contrast, was built not just to function, but to endure. It could run at maximum output for hours, tolerate battle damage, and still bring pilots home. The contrast was painful. Where Japanese engines demanded delicate care, The American engine demanded only fuel and air. Attention then turned to the Hamilton Standard hydromatic propeller, the massive 13-foot, three-bladed device that transformed the R-2800's raw energy into thrust. The propeller alone weighed nearly half a ton, and its size was what had driven Rex Beissel's design team to create the Corsair's iconic inverted gull-wing shape. But it wasn't just large, it was intelligent. The propeller was fully variable pitch, allowing its blades to change angle automatically to maintain optimal efficiency at any airspeed or altitude. For the Japanese engineers, this mechanism was extraordinary. Their own propeller systems were mostly constant speed or manually adjusted, often unreliable and prone to failure under combat stress. The Hamilton Standard propeller's pitch control system, driven by a hydraulic governor, maintained perfect rotational speed under all conditions, ensuring the engine never over-revved during dives or stalls. This not only preserved engine life but also gave the Corsair an unmatched acceleration curve and climb rate. When they examined the propeller blades themselves, they discovered another revelation: the metallurgy. Each blade was forged from high-strength aluminum alloy, heat-treated to perfection, and balanced to an almost microscopic degree. Even after thousands of flight hours and exposure to the corrosive Pacific environment, the blades retained their exact symmetry. The surface finish was smooth, polished, and sealed against corrosion, testament to the industrial chemistry supporting American aviation. In comparison, Japanese propeller production relied heavily on wooden or laminated metal designs, often hand-finished and vulnerable to warping in tropical humidity. Precision balancing was done manually, which meant minor variations could induce vibration and reduce efficiency. The Hamilton Standard system, by contrast, operated like a living organism, self-regulating, responsive, and durable. As the team documented their findings, the broader implications became clear. The engine and propeller together represented not just technological superiority, but an entire ecosystem of industrial mastery. To build something like the R-2800, one needed vast foundries, precision lathes, quality alloys, lubrication chemistry, testing facilities, and a skilled workforce, all coordinated by systems of standardization and logistics that Japan simply could not replicate during wartime. In one internal report, a Japanese naval engineer wrote, "This engine is not a machine, it is an industry. Each bolt and bearing carries the weight of a nation's factories." It was an apt observation. The R-2800 Double Wasp was the living heart of America's industrial strength, designed by engineers, perfected by machinists, and replicated by thousands of anonymous workers who together built the air power that crushed the Axis. The study concluded with a somber note. Japanese analysts admitted that even if they fully understood the Corsair's engine and propeller, reproducing it was impossible. Their supply chains lacked the alloys. Their factories lacked the precision equipment. Their skilled technicians were already stretched thin, repairing the existing fleet. Knowledge alone could not substitute for capability. Engine and propeller analysis. When Japanese engineers at the Yokosuka Naval Air Technical Arsenal finally removed the Corsair's cowling and exposed its heart, the Pratt & Whitney R-2800 Double Wasp, they found themselves staring into a machine that symbolized everything Japan could not replicate. The engine was immense, a twin-row, 18-cylinder radial masterpiece that combined brute force with precision craftsmanship. To the untrained eye, it was just another radial engine. But to the technicians who had spent the war maintaining fragile, temperamental power plants under constant material shortages, this was something transcendent, a cathedral of metal and engineering discipline. The R-2800 Double Wasp was unlike any power plant Japan had encountered. Its sheer presence filled the workspace, every cylinder meticulously aligned, every cooling fin machined with uniformity that seemed impossible under wartime conditions. Producing over 2,000 horsepower, this engine powered not only the Corsair but also the Thunderbolt and the Hellcat, aircraft that had dominated skies from the Solomons to Saipan. As the engineers dismantled its outer components, the deeper layers revealed a kind of perfection they rarely saw even in peacetime Japanese prototypes. The tolerances were exact. The casting of the crankcase, the balance of the pistons, the the precision of the bearings, all spoke of an industrial culture that had mastered large-scale precision engineering. One Japanese report later described the engine as a symphony of standardized excellence. Unlike Japanese engines, which often relied on hand-fitting and individual craftsmanship to achieve tolerances, the R2800 components were interchangeable, an outcome only possible through advanced tooling, gauges, and quality control. This meant American factories could produce thousands of engines with identical performance, while Japanese plants still struggled to ensure consistency from one batch to the next. The engineers were particularly fascinated by the two-stage, two-speed supercharger system, a marvel of mechanical sophistication. It was this system that allowed the Corsair to maintain its performance at high altitudes, where most Japanese engines lost power rapidly. The supercharger compressed incoming air in two stages, driven by precisely machined gears that switched speeds automatically depending on altitude. This granted the Corsair immense versatility, letting it fight from sea level to over 30,000 feet without losing combat effectiveness. When the supercharger assembly was disassembled for closer inspection, the Japanese engineers noted the perfect symmetry of its impellers and the mirror-like surfaces of its inner walls. Such finishes could only be achieved through advanced machine tools and extensive quality assurance, resources Japan no longer possessed by 1945. Even more impressive was the cooling system. The Corsair's engine employed clever ducting and baffles to channel air evenly across the cylinders, preventing overheating during low-speed carrier operations or tropical ground idling. Japanese mechanics were accustomed to coaxing underpowered engines to survive long enough for combat. The R2800, by contrast, was built not just to function, but to endure. It could run at maximum output for hours, tolerate battle damage, and still bring pilots home. The contrast was painful. Where Japanese engines demanded delicate care, the American engine demanded only fuel and air. Attention then turned to the Hamilton Standard Hydromatic Propeller, the massive 13-foot, three-bladed device that transformed the R2800's raw energy into thrust. The propeller alone weighed nearly half a ton, and its size was what had driven Rex Beissel's design team to create the Corsair's iconic inverted gull-wing shape. But it wasn't just large, it was intelligent. The propeller was fully variable pitch, allowing its blades to change angle automatically to maintain optimal efficiency at any airspeed or altitude. For the Japanese engineers, this mechanism was extraordinary. Their own propeller systems were mostly constant speed or manually adjusted, often unreliable and prone to failure under combat stress. The Hamilton Standard propeller's pitch control system, driven by a hydraulic governor, maintained perfect rotational speed under all conditions, ensuring the engine never over-revved during dives or stalls. This not only preserved engine life but also gave the Corsair an unmatched acceleration curve and climb rate. When they examined the propeller blades themselves, they discovered another revelation: the metallurgy. Each blade was forged from high-strength aluminum alloy, heat-treated to perfection, and balanced to an almost microscopic degree. Even after thousands of flight hours and exposure to the corrosive Pacific environment, the blades retained their exact symmetry. The surface finish was smooth, polished, and sealed against corrosion, testament to the industrial chemistry supporting American aviation. In comparison, Japanese propeller production relied heavily on wooden or laminated metal designs, often hand-finished and vulnerable to warping in tropical humidity. Precision balancing was done manually, which meant minor variations could induce vibration and reduce efficiency. The Hamilton Standard System, by contrast, operated like a living organism, self-regulating, responsive, and durable. As the team documented their findings, the broader implications became clear. The engine and propeller together represented not just technological superiority, but an entire ecosystem of industrial mastery. To build something like the R2800, one needed vast foundries, precision lathes, quality alloys, lubrication chemistry, testing facilities, and a skilled workforce, all coordinated by systems of standardization and logistics that Japan simply could not replicate during wartime. In one internal report, a Japanese naval engineer wrote, "This engine is not a machine, it is an industry." Each bolt and bearing carries the weight of a nation's factories. It was an apt observation. The R-2800 Double Wasp was the living heart of America's industrial strength, designed by engineers, perfected by machinists, and replicated by thousands of anonymous workers who together built the air power that crushed the Axis. The study concluded with a somber note. Japanese analysts admitted that even if they fully understood the Corsair's engine and propeller, reproducing it was impossible. Their supply chains lacked the alloys. Their factories lacked the precision equipment. Their skilled technicians were already stretched thin, repairing the existing fleet. Knowledge alone could not substitute for capability. Strategic implications. By early 1945, when the captured F4U Corsair lay disassembled in the hangars of Yokosuka, the war had already begun to turn irreversibly against Japan. Yet for the engineers and officers who gathered around its gleaming blue fuselage, this was more than a technical examination. It was a moment of reckoning. The Corsair wasn't merely an airplane. It was a mirror, reflecting the staggering industrial, scientific, and organizational power that the United States had mobilized across the Pacific. Inside the dim echoing halls of the Yokosuka Naval Air Technical Arsenal, Japanese specialists walked around the Corsair's components with quiet disbelief. They had examined captured aircraft before, P-40s, B-17 fragments, and even parts of AP-38 Lightning, but never had they encountered a machine so perfectly integrated, so consistently engineered. Each rivet, each hydraulic line, each weld spoke of mass production refined to near perfection. The Corsair was not just a product of superior design, it was the result of an entire nation's industrial philosophy. As the inspection deepened, the Japanese engineers began documenting their observations with unusual candor. The reports noted how the Pratt & Whitney R-2800 Double Wasp engine operated at levels of precision that Japanese factories could not replicate even under ideal conditions. Its tolerances were uniform, its metallurgy stable. The twin-stage supercharger system, meticulously sealed and balanced, allowed the Corsair to maintain power at altitudes that Japanese radial engines could only dream of. Every component had been manufactured to exact specifications, something that required not just skill, but a vast coordinated industrial infrastructure. The Hamilton Standard propeller, too, embodied a kind of sophistication Japan struggled to match. Variable pitch systems had existed in Japanese aircraft, but none operated with this level of reliability or efficiency. The control mechanisms were compact, streamlined, and electrically synchronized, a small miracle of design born from abundant materials and skilled technicians. Where Japanese engineers relied on manual calibration, the Americans had achieved mechanized precision. The airframe told an equally revealing story. The Corsair's inverted gull wing, a hallmark of its silhouette, was not merely aesthetic. It was a triumph of aerodynamic logic and practical engineering, reducing drag while allowing for shorter landing gear and better propeller clearance. The curvature of the wings, the flush riveting of the fuselage, and even the combination of aluminum and treated fabric showed an understanding of material science that balanced performance, weight, and resilience. One Japanese engineer reportedly wrote, "This is a machine designed not by individuals, but by a nation." It was an observation that cut to the heart of Japan's wartime dilemma. While Japan had brilliant aircraft designers, men like Jiro Horikoshi, who created the A6M0, their genius operated within a system starved of resources, manpower, and industrial stability. Aluminum was scarce, rubber had to be imported or synthesized, and high-grade fuels were dwindling. Factories were bombed, skilled workers conscripted, and research facilities relocated underground. In contrast, the United States had turned its factories into cathedrals of production, automated, abundant, and resilient. The Corsair's cockpit instruments also astonished the Japanese analysts. The layout was ergonomic and clearly standardized across production runs. Electrical wiring was neatly bundled, labeled, and color-coded, an unimaginable luxury in a nation that by 1945 was reusing old copper wiring stripped from destroyed aircraft. The avionics and radios were rugged, waterproofed, and built with redundant circuits to ensure survival even under battle stress. The Japanese realized that this level of reliability was not accidental, it was systemic. When the final report on the Corsair's analysis circulated within Japan's naval command, it read less like a technical document and more like an obituary for Japan's aviation ambitions. It concluded that while Japanese pilots remained courageous and tactically skilled, their machines were now hopelessly outclassed. American fighters like the Corsair could outclimb, outdive, and outshoot nearly every contemporary Japanese aircraft, and do so with ease of maintenance and replacement parts that Japan simply could not sustain. Even more alarming was the broader realization that the Corsair represented just one link in a vast, unstoppable chain. Behind it stood the Grumman Hellcat, the P-51 Mustang, the B-29 Superfortress, and hundreds of other aircraft, all products of a unified, scientifically managed war economy. Each was built in the tens of thousands, standardized, and continuously improved. The Corsair Japan studied might have been a single machine, but it symbolized an assembly line of power, an industrial rhythm that no amount of pilot bravery could disrupt. For the Japanese High Command, these revelations carried strategic weight. They proved beyond doubt that technological and material inferiority had become insurmountable. Even if Japan could replicate aspects of the Corsair's design, it lacked the industrial depth to mass-produce such aircraft, the fuel to power them, and the logistical systems to support them across the Pacific. The Corsair thus became not just an enemy fighter, but a symbol of inevitability, the embodiment of industrial war's final logic. In a way, the Corsair's capture offered Japan one final gift: clarity. The engineers who examined it saw firsthand what total war had evolved into, a contest no longer defined by individual heroism or tactical ingenuity, but by engineering discipline, scientific precision, and production mastery. It was a revelation that came too late. By the time their reports reached Tokyo, the cities themselves were burning, and Japan's aviation industry lay in ruins. When historians later rediscovered those technical reports, they read them as quiet acknowledgments of defeat, not in battle, but in technology. The Corsair had not merely dominated the skies, it had exposed the structural limits of an empire that had reached beyond its industrial grasp. In the end, the Japanese examination of the Corsair was more than a study of metal and machinery. It was an autopsy of ambition, a final, sobering confrontation with the reality that the war's outcome had been decided not just in the clouds above the Pacific, but in the foundries, assembly lines, and laboratories of America. And as the war drew to its close, that realization, more than any single battle, marked the beginning of Japan's long journey toward rebuilding a new identity from the ashes of technological defeat. Post-war legacy. When Japan surrendered in August 1945, the war machines that once symbolized ambition and defiance lay scattered across the empire, rusting, burnt, or abandoned in the ruins of airfields and factories. The captured F4U Corsair, once meticulously studied at the Yokosuka Naval Air Technical Arsenal, likely shared the same fate. It was dismantled, stripped for scrap metal, or lost in the chaos of occupation. Yet its influence, though unseen, endured far longer than the aircraft itself. For the engineers who had examined it, the Corsair was more than an enemy fighter, it was a revelation. During the war, they had marveled at its sophistication with a mixture of admiration and despair. After the war, that admiration quietly evolved into respect and eventually inspiration. The same men who had once documented every bolt, rivet, and circuit with military precision would later become the architects of a new Japan, one built not on conquest, but on craftsmanship, innovation, and quality. When the Allied occupation began, Japan's industries were in ruins. Airfields were cratered, machine tools melted or confiscated, and the once mighty aircraft factories stood silent. The country faced not only economic collapse but an existential question: how could it rebuild from total destruction? Ironically, some of the answers had already been glimpsed in that single captured Corsair. The engineers who studied it had written detailed reports, sketches, and blueprints, many of which survived the war's end. Within them lay insights into manufacturing discipline, material selection, and systems engineering, lessons that would soon find a new life in Japan's post-war industrial rebirth. In the late 1940s and early 1950s, as Japan began to rebuild under Allied supervision, American influence reshaped every sector of production. Former aircraft engineers found work designing sewing machines, cameras, and motorcycles. The precision required in aviation design transferred naturally into these new civilian industries. The philosophy they had once seen in the Corsair, precision, consistency, reliability, became guiding principles. Out of this transformation emerged an idea that would define Japanese industry for generations: Kaizen, or continuous improvement. The concept wasn't new, but its systematic application was revolutionary. Every worker, from factory floor to management, was encouraged to seek incremental perfection, the same spirit that had driven the Corsair's flawless engineering. The obsession with quality control, meticulous inspection, and production discipline that American aircraft symbolized now took root in Japan itself. By the 1960s, Japan was no longer the nation of wartime shortages and improvisations. Its products, radios, cars, cameras, were becoming symbols of reliability and excellence. Companies like Toyota, Sony, and Mitsubishi applied methods of production that mirrored the very industrial logic once admired in the Corsair's design: precision assembly, quality assurance, and technological integration. The echoes of the Yokosuka examination could be heard, faintly but clearly, in the rhythmic hum of Japan's new factories. Meanwhile, the Corsair itself continued to carve its legacy across the skies. Though the war that had created it had ended, its story was far from over. The F4U Corsair remained in active service through the late 1940s, its ruggedness and power unmatched by early post-war designs. When the Korean War erupted in 1950, the Corsair once again roared into combat, this time against Soviet-built MiGs and fortified North Korean positions. Pilots of the U.S. Navy and Marine Corps praised its versatility, the same qualities that had astonished Japanese engineers years earlier. In Korea, the Corsair evolved from a pure fighter into a fearsome ground attack aircraft, delivering bombs, rockets, and napalm with surgical precision. It became an icon of close air support, earning new respect among a generation of aviators who had grown up hearing of its exploits in the Pacific. The Corsair's ability to adapt, from carrier dogfights to mud-level strike missions, symbolized the enduring power of thoughtful engineering. Even beyond Korea, the Corsair refused to fade into history. It saw combat as late as 1969, during the brief but intense soccer war between Honduras and El Salvador, an astonishing 25 years after its debut. Few aircraft could claim such longevity. The world had moved into the jet age, yet the Corsair's gull wings still sliced through tropical skies, a living relic of piston-driven power and wartime ingenuity. Its continued service testified to something profound: great design transcends its era. The Corsair's structure, systems, and aerodynamics were so fundamentally sound that even as technology advanced, its core engineering remained relevant. It was a rare convergence of art, science, and necessity, born in war, perfected through adaptation, and immortalized in the annals of aviation history. Back in post-war Japan, the lessons of the Corsair, though never officially acknowledged, lived on in subtler ways. The engineers who had once studied it became educators, mentors, and innovators. They carried with them an understanding that true technological mastery wasn't merely about invention. It was about precision, process, and purpose. The Corsair had shown them what disciplined industrial excellence looked like, and Japan, in its remarkable post-war transformation, proved it had learned that lesson well. By the 1970s, the cycle had come full circle. Japanese manufacturers began exporting advanced aircraft components to the very nations that had once defeated them. Mitsubishi Heavy Industries, which had built the Zero, was now producing parts for American aircraft. The Apprentice had become a partner, and the philosophical seeds planted during the war had blossomed into a new era of collaboration and mutual respect. Today, few physical traces of that captured Corsair remain: no wreckage, no preserved fuselage, no museum display. Yet its invisible legacy endures. It exists in the precision of a Japanese camera lens, the smooth operation of an automobile engine, the hum of an industrial robot on a Tokyo assembly line. The aircraft that once symbolized defeat became, indirectly, a catalyst for rebirth. In the grand narrative of history, the Corsair's post-war legacy bridges destruction and renewal. It reminds us that knowledge, once gained, never truly dies, it transforms. The same qualities that once gave the Corsair dominance in war, ingenuity, attention to detail, and relentless pursuit of perfection, became the very principles that define Japan's rise as a post-war industrial power.